Hi everybody. This lecture is about network servers, and it is a continuation, a companion piece to the previous lecture on network clients. So in this one, we're going to be talking about setting up the network sockets that are based in our servers and connecting the clients to them. We're going to demonstrate the working server code, which is the other half of the code that works with the client we demonstrated last time. We're going to talk about some different ways to run a server with concurrency, that is, being able to accept multiple connections at once. And finally, we'll talk about how do we know when data is actually available to be read or written. So first, let's look at an overview of a non-concurrent server connection. So this would be a server that is handling one connection at a time. So when we have our server with its IP address, it is listening at a particular port. So we might establish port 80 for our particular socket that we've previously created. And maybe we've got connections coming in from these three clients. From 192.168.1.2, here we have two connections from that particular IP address, that interface. This one is from the port 3874, this one's from 58411, but both are coming from the same IP address. Here we have a IP address 192.168.1.3, so it's a totally different IP address, which generally means a different machine, a different host, but it has the same port as this other one. So the server socket is going to listen on a specific port, and many different clients will be connecting to that port. The server has to be able to differentiate between these and communicate with each one as needed. So the first thing that the server is going to do is it's going to choose the next connection that it's going to deal with. So imagine it takes this one, and generally speaking, choosing the next connection means taking there's a queue of them all ready to go, and it pulls the next one off the stack and starts working with it. Step 2 is the server is going to create a new file descriptor for the chosen connection to use. So this will be a file descriptor that is exclusively used for this particular connection. The port does not change. We'll talk about how that works in a bit here, but essentially the server is going to create a brand new file descriptor that's only for the connection that it's now processing. Step 3 is that with that established, the client will begin to communicate with the new file descriptor that was created by the server. So now, new connections can be handled again by the listen socket FD. So that brings us back to the beginning. So how does it tell the difference here? Well, the operating system's network layer that's on that server is going to be able to tell the difference between each connection by what's called a 4 tuple. So 4 pieces of information. And it will use these to route the network packets to the correct socket and to the correct file descriptor for usage by the program. And it will do that based on the server's IP and port mixed with the client's IP address and the client port. Those 4 pieces of information define where the data goes to which port on this particular server. So any packet that arrives that has those 4 settings the same as another one is coming from the same connection or going to the same connection. So for our API here, for the server-side sockets, we're going to create the network socket, which establishes a file descriptor, with this socket call, the same way that the client does. So we have to create that file descriptor at the beginning as well. Then we're going to bind that socket to a particular port number, and we'll do that with the bind function call. Then we'll start listening for connections on that socket with listen. That makes this system be alive. It makes it able to start receiving connections to that port for this process on this machine. In order to actually process those, in order to actually get data from them, you have to call accept. So you put this in a loop and you call accept repeatedly over time, which is going to connect these incoming connections to new sockets, which are new file descriptors, for each connection's exclusive use. We're going to read and write data then to and from this newly created socket. And we can do the classic send and receive, or even read and write if we want. So to create the socket, we're going to do this in the same way as the client. This is the exact same slide with the same parameters. We are going to specify, we want to do a TCP connection, and we want to use a full-blooded AF INET socket, and we'll check the return result for -1 and pass any flags if we have any. to fill in the address struct for the server, this is also the same, with the one exception being that we can specify the connections or where they can come from for the server. And in this case, we'll use inadder_any down here. This just puts in the fact that we will be able to anticipate connections from any particular IP address to this server. And if you remember, the htons function here converts this 80, which is a number that you and I understand, and converts it into something that the computer can use, essentially from the least significant byte storage method that the PC uses into the network order, or where the most significant byte is first. AFINET, this is the same thing we talked about before, where you're specifying what kind of connection we're making here, or what kind of socket we're going to use. Alright, so the next step is to bind the socket that we've just created to a particular port. So this is going to allow multiple processes that are running on the single machine to communicate across the network from only a single IP address, just as that first bullet point says there. So this is how we enable the system to be able to listen to and respond from a particular port. So the server, it needs to pick a port where the clients can actually can contact it on. So bind takes the port with the socket that's already been created and does the magic and registers with the operating system that that particular port is now in use for this process. If another process tries to call bind on a port number that's already been allocated, then that bind call will fail. Here's an interesting point here. Even after you've closed all the sockets down, the operating system does not immediately let go of the port. So even though you've closed your program down and everything seems to be shut down, it might be several seconds, it might be several minutes before that port becomes available again. The operating system doesn't garbage collect immediately that that port was just recently used, which is okay because there are 65,000 different ports that the Unix operating system can choose from to use. So chances are you'll be able to find another one that works. So to bind the socket, this is the call for it. Bind takes the socket that we've previously created, and then we're going to bind to this port. Then the address, this is where you take the address struct that you've previously created that designates which port, and then the length, the add length parameter on the far right is the size of the address structure. Down below here is an example of this in action. So here's bind, here's the listen socket that we've created, here's the server address being cast into the appropriate format, and the size of it, and test for errors at the end to make sure it actually succeeds. And it will frequently not succeed, so make sure you put this in there. And the reason why it won't succeed is 9 times out of 10 that port's already in use. Alright, so once that's done, we can now listen for connections. The server is going to ignore any connection attempts until you tell it to start. So you have to call listen or else nothing actually works. So once you've done that, then the socket starts to queue up connections. So data won't start flowing until we call accept, which is the next step. But in order for the connections to be ready to go, they have to be they will queue up because of the listen call that's been made. So you listen for a particular socket that's been previously created and bound to a port. And then for the queue size, this is where we're passing in how large of a queue so how many different connections should this socket be able to accept at once before new connections are refused. And again, here, let's go ahead and do some error checking based on the listen call and make sure it returns successfully. So, as we alluded to just there, we accept to actually enable information to flow. And you put this in a loop. So the server is, generally speaking, a program that runs for a longer term duration than a client, and it just waits for the clients to contact it. So the server has an infinite loop that is just continually processing connections from the clients. The accept function is going to take the next connection off of the listen queue for that socket. And it's going to present that as something that can now have data transmitted through or from. And if there is not one available, accept will block the process until a connection request arrives. So normally that's all right for a server whose job is to sit there and wait for connections to arrive and then process them. It's okay for accept to be a blocking call because it doesn't have anything else to do anyway. So here is the example for accept. So accept is going to return -1 if something bad happens. Here, socket is the socket that we're going to get a connection from, and the address is where we put in the network address struct, and this is where the client information will be written. So this isn't something that you are putting in as data that you're filling out beforehand. This is where the client data gets written into once the connection is established. And then finally, the size of that particular address. Now, what this function returns, certainly -1 for error, but it also is going to return a file descriptor for the new connection. As we talked about at the very beginning, the data will only be transmitted through the socket using the new file descriptor that accept returns. All communication for this particular port through this particular established connection can only flow through that socket, not through the one that you're listening on. So down here we can see that the accept is returning as a result to the established connection FD variable, and we can then test that to see if there was an issue. This is the socket that we actually use then later. Client address is where the client connection information is written into. So here is the companion piece to client.c from the previous lecture. Let's take a look at it. Up here are the include statements that give us all the libraries we need for this particular program. Here's our error function, just like in the previous one. We use this to print errors and then exit. Main function starts. Here's all the variables we're going to use in this program. We're going to check the usage, which means we're going to look at we're going to make sure that we have all of the user input that we need to run this program. So in this case, we need to know the name of the program and then the port. That's how we use this particular one. So give me the port number so that we can bind to it later. Here's where we set up the address struct for this process on the server. So memset out our server address, get the port number that the user entered, and then build up this address structure. So take the port number, convert it into the special format we need, indicate that the ports that we will accept connections from are any with this in adder underscore any variable, and then set up our socket. Just call socket, and we're going to be doing that to just create the socket that we have, and we're going to set that return result equal to our listening socket. Once we have a socket and we have a server address variable all created, then we can, on this page, we can call our bind call. This is going to take the socket that's been created, the server address, which is defining the ports we'll accept connections from, the type of socket that we're willing to use. It's going to take all this and bind the port to the socket to enable us to use that later. Our next line is simply listen. So now we're turning this particular socket on. We're ready to go. Any connections can now be established to this server. No data flows yet, but at least the connections can be made. All right, next we're going to accept some connections. And in order to do this, we need to take our client address variable. We'll get the size of it and store that for a moment. And then in accept, we're going to pass that size in, pass in a client address variable that we're going to be writing data into. It has to be cast to the same type. And then pass in the listening socket that we are using. This is the socket that we've previously created, the one that's been bound to a port. Down below, in order to prepare for the connection, we are going to, well, let's take a look at this accept. So what accept returns is this established connection file descriptor. That's where the data is actually read from and written to. So down here, we're going to memset out our buffer to clear it out. And if you remember, our client is sending data in the beginning, so our server has to receive. So here the server receives from the established connection file descriptor, stores it into the buffer, and note that here I've got 1 byte less than the size of our buffer because we want to keep a null terminator in the end of this thing. Verify that the number of bytes that we're reading is what we expected. In this case, I'm just checking for error results, but you can imagine that in here we would also put in something like if it's 254 or 253, then maybe we have some sort of error result. This is where you do that check. Print out that the server received that information from the client, and then send the success message back to the client. This mimics what the client did sending to us originally. So send this message back, and then verify that in this same variable that we're using here, that we were able to successfully send. close down that established connection file descriptor, and then close down our listening socket, and then exit the program. So that is our complete example for the server. Alright, so as the results here show, we can see that we can compile both programs. Here for the server, I'm setting up this server to run at this particular port in the background. And that way I still retain access to my command line so I can play around with the client. Here I fire up the client with the existing machine that I want to use, which is my own machine. So localhost, and then I pass in the port number, and that enables the client to connect to the server. Then, just as we saw before, the client asks me to enter in some text, which I do. The server says it receives that message, prints it out again, and then sends back to the client that it received it. And it says, I'm the server and I got your message. The client prints that also out, and then it terminates. And then we receive this notification from Unix that the server has also terminated, because if you remember at the end of the server, it doesn't do anything else. It doesn't go into a loop. In our example here, it just exits. And that's the end of our test process there. So this particular server example is going to live forever, and it's going to do that by wrapping the except section in a while loop. So this will also work with client.c that we've talked about in the previous lecture. So all the code here is the same. Let's take a look at this second page. So once we've listened for our socket, we're going to start up a while loop. And in this while loop, we are going to terminate the while loop down here after our established connection file descriptor is all done. Then we're going to indicate to the user that the server has a connected client at a particular port, and then this is a function that we can use to translate the host orders back to the network order. Actually, it's network to host order, and this is going to be from the client address variable that was written to by accept, get the port out of it. So we can tell which client or which port this new client connected in on. And this loop runs forever. So essentially, it comes in, it is going to run accept, and once accept has been called, it returns an established connection file descriptor. That file descriptor then does the read and the write routine, and then loops back up to the top after closing it all down. So this will continually run, accepting, pulling a connection off the top, managing the transaction, and then returning back up to the top. So this is our multi-server example. So as far as the example of this thing running goes, here's how that works. Here's our multi-server that we establish on a particular port running in the background again. Fire up the client at localhost, target the same port. This time, I go ahead and enter in some text, and the server reports that the connected client has come in at port 38422. Now, nowhere have I indicated this port. This is a port that Unix chose for my client's outbound connection to hit the client's or to hit the server's 55556 port. So note that we didn't pick that. That is given to us by the server, which is a good thing because it picks a free port for us to use. Now you can see how these lines are all combined on the same actual line. It looks annoying, it's hard to read, it's hard to decipher, but what's happening here is that the client and server are both sending text to the terminal, and that can be kind of hard to control. So be aware, you can't really control when things are going to be read and written to your terminal, which can play havoc with the output. Once that's done, however, I type in my test, and the same process goes back and forth as we saw before. We see data go back and forth. The server does not shut down, though. Now I can establish another client, send a different set of text, so much text in this case, and get the same thing back and forth with the server also sending its special notification message. And once I'm all done playing around, I can kill off multi-server by sending a terminate signal at it, and I get the notification that it is in fact gone. Alright, so let's talk about doing it all at once. Many clients are going to need to connect and perform tasks at the same time. We don't want an iterative server that only handles one thing at a time. By realizing that, we are realizing that what we want to minimize is our response time. We want a server that's fast, that always seems to be on the spot, always seems to be receiving our data and handling our connection. We want to minimize the complexity. We don't want to constantly be pulling for data to see if anything's there. We want to maximize throughput, which means we want to be able to service as many connections as we can per second. And we want to keep our hardware fully utilized. So don't waste any time. Let's process as many connections as we can so that we can get the most bang for our buck out of the hardware. All these things are trade-offs. So let's take a look at a couple of methods and see if we can come up with an example for the Unix system that demonstrates all this together. Let's talk about the iterative server, just as a backwards look at it. The iterative server handles one connection at a time, one client at a time, and it's non-preemptive. That's the buzzword here. The additional clients are all having to wait for previous requests to complete. They're easy to design, they're easy to implement, easy to maintain, but they're only useful for when that request processing time is going to be short. So that implies that the service being performed by the server is minimal, or not particularly complex. So not typically going to be using input and output that's going to block the server for a while. So, and we also might introduce an iterative server if the order really matters. So we really do want to handle things in the order they came from and no faster. Leaving that, we look at the concurrent stuff. So concurrency is going to be provided in two ways, either apparent concurrency, so fake concurrency, or real concurrency. In the apparent concurrency, we are talking about a single thread of execution, and we're going to use the select command and non-blocking input and output. And we'll talk about select a little bit more here in a bit. Real concurrency means multiple threads of execution, or multiple processes, which each have a thread, or maybe more than one thread, but we are actually going to be doing multiple things at once. So this example that we've seen before on the right, we've got some chat server that's trying to deal with users connecting and disconnecting, that is trying to send output out, and is trying to receive input to distribute everywhere. For apparent concurrency, let's take a look at some of the details. There is really only the one thread. It's a fake concurrency after all. There's no preemption. We're not going to use non-blocking I/O because that would stall everything. So whenever an input-output request comes in that would block, so read some giant file off the hard drive, or write something down to the hard drive, then go ahead and just switch to another connection. Don't actually do it. Just so kick off the connection and switch to something else. Up to a certain number of clients that are being served, this is going to maximize our CPU utilization. So this is going to increase our throughput drastically. So whenever that I/O request comes in, just go ahead and do the I/O request, but don't stay there on that process. Switch to something else. So the complexity that this obviously gives us is that we have to track all the connections that come in, figure out which one to run next, detect when the blocking calls are coming in, that kind of thing. It works pretty well if the requests are short, if we know that we are going to be switching off based on a limited number of connections that come in, and if our request time is short, we know that we're never going to have to stall for too long. So for real concurrency, we are talking about a preemptive system. So the clients can connect at any time, and we're going to use multiple threads or multiple processes to service those connections. And out to a certain number of connections, this is going to maximize our CPU time. It's going to maximize the response time and increase our throughput. But it is harder to design, it's harder to implement, and it's harder to maintain. After too many concurrent connections, everything slows down because you're processing more connections at once. The server eventually hangs. There is just not enough time to be able to deal with all of the constant connections coming in and out. You spend more time managing connections than you do actually processing data. So we have to put some sort of limit on the number of concurrent connections at any given moment. This kind of concurrency is far more common than the apparent concurrency we were looking at before. So there are 4 typical ways to produce this real concurrency. So briefly stated, we'll create one process per client connection, create a pool of available processes before the clients connect, and then use those as they do. And then we can use just one process and either have one thread per client connection, or in that one process have a pool of available threads that are previously spun up for those clients to use when they get here. Looking a little bit closer, Our first solution here is to have one process per client connection. Pretty easy to understand. We don't have to worry about much of a shared state to worry about between them. Every time we get a new process, we just fork the process, fork the entire server out to another connection, and handle it in the server code. The primary disadvantage is that process creation via fork is really slow. I mean, on the order of an operating system being slow, of course, but it's comparatively slow. Context switching between processes, so switching between the different processes as they come in and out of the CPU, is also slow, but it's nothing compared to how incredibly slow fork is. So the other solution for fork here is to create a pool of available processes that are ready to go. This pool of processes has a set of processes that are reusable, so they don't just terminate after they're done running, but they're available for us to repurpose. The nice thing here is that we get rid of the fork issue, where it takes so long to fork out a new process. We get a much more rapid response as long as there is an idle process. We can set the pool size too, so that we don't overload the hardware. And if we just need to get the program running quickly out of the gate, we could spawn, say, a limited size of a pool just to get it going, and then have a system where, as connections come in, we create new pool threads until we have a maximum size of the pool so that we don't overload that hardware. Disadvantages: we still have process context switching happening, and we have to manage a pool of processes, which is not really trivial. The other solutions are going to involve threads, where we have multiple concurrent execution contexts within a single process. That means multiple connections at the same time in the same process. We could do this as a server, as a single process with multiple threads, where each thread is a connection, so it handles its own new file descriptor from accept, or a pool of threads that are being passed in handles addresses to these new file descriptors that are spawned by, say, the parent. In either case, our advantage is that we're going to trade our process context switches, which are comparatively slow, for thread switches, which are a lot faster. And we share all the address space. We've got all of our code and data, and all the variables are accessible between all the threads, which is a really nice advantage. Our code has to be thread safe, though, so that's something we have to worry about. And we also have to worry that we're not sharing data that we don't want to share. But for the most part, this type of thread solution, with maybe some minimal process forking for truly other purposes that the server is doing, is generally how things are done. All right, let's look at select here as our final topic. So select is going to be used for server-like applications that have many communication channels open at once. So for example, imagine we are trying to minimize the delay between when data or when space becomes available before we do something, and that data or space could become available at any time on any of the channels that we are looking at. So from the high-level perspective, we're going to call select with a list of read and or write file descriptors, and select will return when any one of those descriptors becomes readable or writable, which means it is a blocking system call. Here is the usage of this thing. So select, we've got a ton of different variables that go into this. The top one, NFDS, is the highest numbered file descriptor plus 1 that we're going to be using. So remember that we're passing in a set of file descriptors that we care about. So figure out which one is the highest numbered and then add one to it, and that's what you put into NFDS. Then read, write, and error file descriptors, these are pointers to this struct called, or this data type, which is fd_set. And these things are bit masks. So each bit of this variable, it refers to one of the file descriptors. So bit 0 is file descriptor 0, bit 1 is file descriptor 1, etc. So we can track file descriptors as being individual bits. So Unix is going to give us some macros to manipulate our bit masks here. So fd0 will set all the bits to 0. Our set, fd set here, sets one specific bit to 1. We can use the isSet function to determine if a specific one has been set to 1, and then we can clear a specific bit also with fd clear. So select is going to return -1 if there was a problem calling it. 0 if it times out, so nothing was actually returned before our timeout occurred, and that's our last parameter here. So timeout is going to be how long it's going to sit there and be blocked waiting if nothing's happening. The other return result out of select is going to be the number of file descriptors that are ready for reading or writing or have had errors occur on them. So here is our select demo. This one comes right off the select man page, so you can take a look at it there, or here where it's nice and pasted and colorized and commented and has nice spacing between everything. So in this particular example, we set up our set, our file descriptor set called readFDs. Then we have a time val struct that we're going to use to track how long we're going to wait. We have a return value here as an integer. We are going to take our read file descriptor set and zero it out, which means that we're not paying attention to any read file descriptors. Then we're going to set file descriptor 0 as the one that we want to pay attention to. Now, file descriptor 0, of course, is standard in. So we're saying the only file descriptor that I care about is standard in. Tell me when this thing becomes available. So this is an improvement. So instead of having to pull that file descriptor or to pull a read command in a non-blocking I/O sense to see if it has data available for us, we can just call select and then stall there and wait and let this thing sit there until data becomes available, which is much better on the CPU because the CPU can go off and do other things. Then we're going to set up our time to wait variable, and we're going to set seconds to 50 and microseconds to 0 here. Then we'll call the select. So I am saying that we are caring about 0 plus 1 is the highest. So 0 is the highest number file descriptor we care about. Plus 1 means that our first parameter for select is 1. Here's where we pass in the read file descriptors, so an address to our struct, and then or to our data type. And then for our writing file descriptors and error file descriptors, I don't care about anything happening on those, so we'll set them to null. Then pass in the address to our time to wait variable, so 50 seconds. So this thing starts running and just sits there. It'll wait there for up to 50 seconds. Once it returns, we take a look at the value here. If it was a -1, then we know something bad happened with select. If there was a non-zero return value, then that means it's a number of file descriptors that are ready to be that have data that we can read from. So data is now available. We'll print out to the user, and we now know that the readFDs variable that we passed in, it has been written with bit masks that show us which of the bits are interesting. So remember, bit 0 was file descriptor 0 and bit 1 is file descriptor 1. We now iterate through this variable, and looking at each bit using the fd_isSet macro to test each one to see if it returns true. And if it does, that's the one that the return value of select is indicating. In our case here, since we're only looking at one, we would expect that return value would say 1 as its value, and we're expecting then that file descriptor 0, since it was the only one that we told it to care about, is going to return true as a result of calling fd_isSet on it. Otherwise, the other possibility is 0, which means no data was returned within 50 seconds. So a great example that was on that man page. One of my favorites of all the examples that's actually listed on a man page. Alright, so as I was writing this code and trying to get it posted into the slides here to test it out on the to paste it from the slides into Vim, it was causing havoc. Every time you post in these double slashes as part of the comments, Vim tries to interpret those as multi-line comments and then wrecks the output of the code for you. So as my first try, I went ahead and typed in this particular command, which is going to globally replace all of the slashes in the file. So what I did is I changed all of the double slashes into single slashes and then pasted it into Vim, which worked just fine. Then with this command, I changed all of the single slashes into double slashes. And it looks awful, but it worked. It worked the first try. I swear I ran this thing the first time and it worked. So when I told my wife this, she was sleeping on the couch, and I woke her up and said, "Amanda, listen to this command I typed. $%s/\_/\_/\_/g." I said it worked the first time. She was very unimpressed. She told me she was very sarcastically proud of me. But anyway, I was very proud of the command, and I'm glad it worked out. Well, as our results here are going to demonstrate, this does work pretty well. Here's the make FIFO command, which establishes our FIFO, my FIFO. Then we are going to take that select demo that we had just looked at in the previous slide, run this thing, and as input, we're going to open it up with my FIFO as where it's going to be getting data from, and we're going to run all this in the background, and it tells us where which job number it is, job 1. Then I'm going to echo some text out, and where is that text going? It is going to my FIFO. And when it does that, the FIFO will route the data through itself into the select demo. So it hooks the output of the echo command into the input of the select demo program through the named pipe. And as soon as both ends are opened, the data gets transferred. The data is transferred through the pipe. Our select call returns, the data flows, and then our select demo ends. So echo through the myFIFO ends at our select demo. All right, well, I think that does it. If you have any questions, please let us know online, and we'll see you there. Thanks!